You may not often think about the words fun and physics as going together, but I want to change that. Okay, what we have to do here is, in order to talk about what is happening in the solar core, in the center of the sun, we have to put some physics out on the table. So we're going to do that right now. The first thing we need to talk about, use pink here for the labels, is nuclear. That's not nuclear, by the way, it's nuclear. Nuclear fusion. Okay? We need to talk about nuclear fusion, because it turns out that is what's happening in the center of the sun, whatever that is. Well, let's take it one word at a time. Nuclear. Okay? Nucleus, right, is made up of protons and neutrons. Protons. Symbol for proton is a P with a little plus. So the nucleus of the atom is made up of protons and neutrons. And of course, you've seen the little pictures of the atom, you know, got the little electrons zipping around it, right? So these are all little electrons zipping around the central nucleus. What we're interested in here is what's happening in the nucleus, which is a collection of positively charged protons and neutral neutrons. It all happens in the middle of the atom. Okay? Now, I've not drawn this to scale. Okay? If the nucleus were the size of, say, a ping pong ball, okay, then the atom would be the size of the city of Decatur. In other words, compared to the size of the electron orbits, the nucleus is a remotely tiny point. So this is drawn way out of scale. So it's about 100,000 times further across an atom than it is across a nucleus. You can line up about 100,000 nuclei across an atom. 10 to the fifth. That's huge. It's a huge difference. So that's the first thing to remember. That what we're talking about is nuclear has to do nothing with electrons. We'll talk, electrons will come into play later on. But nuclear fusion has nothing to do with electrons. It has to do with the nuclei themselves, which are collections of protons and neutrons. So I've drawn it like one thing here, but really it's a bunch of protons and neutrons all stuck together. And that's what makes the nucleus. And that's where virtually all of the mass of the atom is as well. Okay, it's in the nucleus. So that's the first thing to get straight. So that's nuclear. Fusion means building up things, fusing things together to make something bigger. So nuclear fusion is when you take two nuclei and bring them together to form a single larger nuclei. So what you basically get in general is, you know, nucleus 1 plus nucleus 2 becomes nucleus 3, which is larger than the nucleus 3, not nuclear 3. Becomes a new thing, a new larger nucleus, usually plus energy. And when we say energy, we mean light. Not necessarily visible light. Gamma rays is what we really mean. Gamma rays is a form of light that it's made up of the same stuff as light, but it's really high energy and our eyes can't see it. Okay. So when we say energy, what we mean is light. What we mean are gamma rays. They're dangerous to us. They're not good for our bodies. They tend to rearrange our DNA, which is bad. Okay. Gamma rays. It's okay inside the sun, not okay where we live. But basically the point I'm trying to make is that it's a nuclear fusion is a reaction where you take two smaller nuclei and bring them together to produce a new nucleus that's larger than either of the original two, plus you get some energy out. And maybe some other particles too occasionally, as we'll see. So that's nuclear fusion. Okay, that's the first thing to get across. The second thing to get across is that mass and energy are equivalent. And remember, when I say energy, I mean light, which has no mass. Right? Light is massless. Okay, whatever light is, it doesn't have any mass. But you can convert mass into light or energy. Remember, light, energy, same thing for us. You can convert mass into light, and you can convert light back into mass. That's right, stuff. Like stuff you and me are made up of. Protons, electrons, neutrons. All those things can be converted into light. And light can be converted back into those things. Okay? And the equivalent statement is one that you've probably seen before. It's probably the most famous, certainly the most famous physics formula ever. Energy equals mass times c squared. C squared, c is just a number. C is the speed of light. It's 3 times 10 to the 8th meters per second. It's just for our, just know for our money, it's a number. Okay, so it's a fixed number. So c squared is also just a fixed number. The point here is that you can convert energy into mass and mass into energy. That equal sign means that the two are equivalent to each other. It's a major, major insight of Einstein's relativity theory. Mass and energy are equivalent. Okay, and the total amount the sum of mass plus energy cannot be created or destroyed. This is known as the conservation of mass slash energy. You might have heard that you cannot destroy mass, that you can't create or destroy stuff, mass, but you can, as long as you replace it with energy. So the sum of mass and energy, that number can't be changed. It's always the same. So conservation of mass and energy is a big deal. If you lose mass from the universe, you must gain an equivalent amount of energy. If you lose energy or light from the universe, then that must be replaced by an equivalent amount of mass. It's like having two buckets, okay? One labeled mass, one labeled energy. And you've got a certain amount of water in each bucket. You can pour water from one bucket to the other. You can convert mass to energy or energy back to mass. Or put it another way, you can convert light to mass or mass back into light. Okay, but you've always got the same total amount of water. You might have more or less water in your mass bucket, but if you lose water from the mass bucket, it's because you gain that much more water in your energy bucket. Okay, total amount stays the same. Total amount of mass energy remains the same. In fact, oftentimes physicists simply think of mass, that is stuff, as simply a very concentrated form of energy. Okay? They are equivalent. All right? So remember these things. It's all going to come back. These are sort of just little bits of information we're going to be coming back to as we talk about what's happening in the sun. Okay, because nuclear fusion is happening in the sun, and there's a huge conversion of mass to energy happening inside the sun. This, as we'll see by the end of these lectures, all that light, all those watts, you know, the huge light bulb that is the sun with no plug, all that energy is coming from the loss of mass. The sun is losing 4 million tons of mass every second of every day for the last 5 billion years. Every second it loses 4 million tons of mass. It's converted into energy, as we'll see. That is ultimately where the energy comes from the loss of mass in the universe. 4 million tons, actually 4.3 million tons, but who's counting? Per second, gone from the universe converted into light. Good for us, right? We need light down here. Last thing I want to say is that there are 4 known forces in the universe. Okay, 4 fundamental forces. I'm just going to name them right now. We'll say more about them later on. 4 fundamental forces in the universe. Number 1, very familiar to all of us, gravity. Number 2, less familiar, but you experience it every day, you just don't know this maybe, is the electromagnetic force. Okay. Electromagnetic force. All forces that you have experienced your entire life, frictional forces. You know, you hit a baseball with a bat, the force, that force there, the force of your feet on the floor, right? Like contact forces, pushing together, pulling apart, tension inside of strings, whatever. All the forces you are consciously aware of that are not gravity are electromagnetic. There are 2 other forces that only act within the nucleus. Inside that little bitty speck inside of every atom. The last 2 forces only act there, and they are called, believe it or not, the strong nuclear force, and get ready for it, the weak nuclear force. Weak relative to the strong one. Now these forces, without them we couldn't exist. Without them, matter as we know it could not exist. But we don't experience these forces on a conscious level at all. These 2 forces are the ones that really play a major part in the nucleus. Okay? And different kinds of particles are affected by these different forces. We'll meet the particles involved next, and we'll talk about which particles are affected by which of these 4 forces. Okay? Again, we're building all this up to talk about what's going on inside the sun to produce the energy, that 4 times 10 to the 26th watts, and all the energy that you and I have ever needed, and all the living things on the planet need. That's what we're doing here, right? So next up, we're going to talk about the particle zoo. Okay, we talked about another kind of zoo a couple days ago, but next up is the particle zoo. We've talked about protons, electrons, and neutrons. Turns out there's several more kinds of ons out there that are important for us. And those ons are up next.